and welcome to the third video in the series on moments from the Year 2 Mechanics course. And in this video what we're going to do is take all the ideas from the first two videos and put them into the context that you tend to see on exam questions, which is ladders and pegs. So by talking about pegs, what we're talking about is just kind of circular shapes that our rigid body, our rod, is going to be leaning upon, and you'll see what I mean later on. So here we go. First thing we need to do is think about the ladder leaning against the wall. And sometimes, like I've put up in here, sometimes the wall will be rough, sometimes smooth, but in this particular example I'm going to go through, the wall is rough, which means friction is going to appear. So what we're going to do is just think about all the forces that are going on, and then consider the moments of those forces upon the ladder. So, forces acting on the ladder. So we've got a reaction force coming from the ground, and we've got a frictional force to stop the ladder slipping along the ground. And then at the wall, we've got a reaction force there. Now, I've called this reaction force R, so I'm just going to label this one as S, because it's different. And same with this one here, I've got friction here, but I've also got friction at the wall. Now, that frictional force at the wall stops the ladder slipping down the wall, so that means friction is going to be acting upwards. And so I've just called that one G. And the other force I've got there is the weight of the ladder. Now, those are the basic forces I've got going on, and sometimes in an exam question you'll get people standing on the ladders and other bits and pieces going on as well, but in its simplest form, that's what we've got. Let's just have a look what that means in terms of equations and moments. So what I'm going to do is, let's just say for now that this ladder here has got length 2a, and that by calling that 2a just means that we're going to have to deal with this distance here, which so by calling that 2a, just the distance from there to the middle of the ladder makes that a, just makes life a bit simpler. It might be you've got to do that yourself in the question. If you're not told the length of the ladder, then you'll have to just come up with your length. And like I say, that's the easiest way to do it. And we've got an angle between the ladder and the floor, which is theta. And I've just put that theta in up there as well, because you can see we've got an alternate angle, a good old-fashioned Z angle. So clearly, this angle here is going to be theta as well. So, what equations can we form? Well, let's take moments around the base first of all, and let's consider what moments are going to be going clockwise. Well, the clockwise one around the base clearly, is going to be S. That's going to force us to go that way, and also G is going to be a clockwise moment. So what's going on with S? Well, we need the distance from the line of the force to the point that's the pivot, that's the where the moment is happening. So I'm going to put in some extra lines to help us figure all those bits out. And so, first thing we've got is the distance from the line of this force S to the red circle here is going to be that distance there, and hopefully we're happy that is going to be 2a sine theta. We've got theta there, that length of the ladder is 2a, so this distance here, opposite, that's going to be 2a sine theta. And what's going on with G? Well, the line of the force is vertical here, so we need the distance from the line of the force to the moment, so that's going to be this horizontal bit down here. And so if we look at that angle there, theta, that gives us 2a cos theta. So what we've got is S, the force, times by the distance, plus force G times by the distance. And that's the stuff that's going clockwise. What's going anti-clockwise? Well, the one going anti-clockwise is going to be W. So what have we got? Well, we need, again, the distance from the line of the force to the moment is going to be this horizontal distance along here, and that's going to be a cos theta. So there we go. So there we got our moments around the base. If we apply the same principles and now consider the moments around the top of the ladder. So let's see what we've got going on clockwise around the top of the ladder. Well, the ones we need to be looking at here is going to be F and W. So we've got F times by 2a sine theta, again because what we want is the line of the force is here. So if we're looking at that angle there, we've got 2a sine theta, because that's the opposite side to it. And then we've also got W, and I've extended this, so we've got the line of the force of W. And so if we're looking at this triangle at the top, that is going to be a cos theta. So there's the clockwise moments. And then the anti-clockwise moments, that's going to be coming from R. So we can see the line of the force is always already there. So we've got R times by 2a cos theta. And there you go. There's our moments. You have to view these things as if you imagine almost like taking this and rotating this whole diagram so the ladder becomes horizontal, you can see why we're dealing with with these forces or angles and where these lines of forces are coming from. So it is a slightly different idea, because up till now we've been dealing with uniform rods that have tended to be horizontal. Now that we've got the rod on an angle, or the ladder on an angle, then we've just got to think a little bit more carefully about the perpendicular distances. So if I was you, I'd probably take a moment just to pause the video, have a look through, make sure you're entirely happy where each bit has come from and where these horizontal, where these distances from the line of the force to the moments are coming from. And if you're happy with that, crack on. And there's another couple of equations we can form. And the first one we've got is resolving forces vertically. Again, we're not involving moments here, we're just saying, hey, what's going up compared to what's going down. So in the vertical direction, we've got R plus G going upwards and W coming downwards. So R plus G equals W. And if we resolve horizontally, what's going on horizontally? Well, we've just got the friction force here, the reaction force up here. They're the only horizontal bits. So we've got S equals F. Right, so those are your basic equations. And just note as well, because we're dealing with friction, what we'll tend to find is that friction equals mu r is going to be involved somewhere along the line as well. And conceptually, not that much of a problem, but essentially the problem then becomes, because we've got 4 equations, for me personally, I'm never 100% sure exactly which one is going to work straight at the start. So what I tend to do is just kind of belt them all down, get them all in place, and then start having a look at how we can start linking equations together and using them to be able to eliminate certain things and keep hold of other things, and so on and so forth. And we'll see this in the next example. So here's our ladder. Resting against a smooth wall, so straight away we know we haven't got any friction going on at the top of the wall. And let's get some information onto there. There's theta. Tan theta equals 3, so I like to just get all this stuff out of the way early doors, so that gives me root 10 there. Sine theta is 3 over root 10, cos theta 1 over root 10. Not sure if I'm going to need them or not, but I'm just going to blast them down. So I've got that bit dealt with. What forces have we got going on? Well, we've got a reaction force of the wall against the ladder. No frictional force, as I mentioned. There's our reaction force on the ground, and there's our frictional force, and the other force we've got is the weight of the ladder, and it's a uniform ladder, so that's acting through the middle of the ladder. So let's just say let the length of the ladder be 2a, and that's that bit sorted. And what we need is the coefficient of friction between the ladder and the ground. Right, okay, let's start off with the easy bits, and for me the easy bits are resolving horizontally and vertically, so let's resolve vertically first of all. And clearly we've got our upward force, their reaction force, is equal to 20g. That's that bit done, nice and simple. Let's now resolve horizontally. Well, that one is even easier. We've got S going that way, we've got friction going that way, so we've got that. Now, we are aiming for the coefficient of friction between the ladder and the ground, so we're going to need F equals mu r somewhere along the line with this. And so what we've got is friction equals 20 GU, because we've got R here equals 20G. So that's all nice and straightforward. Now let's have a look at what's going on with the moments. Now, it seems slightly weird to take moments about A, because we need the frictional force. And by taking moments about A, we're going to kind of eliminate that. But as you're going to see in a second, it is actually going to, by taking moments about A, it eliminates 2 things and makes it actually simpler to work with. Because what we're going to end up with is equation in terms of S, and you can see already S is linked to friction within here. So let's take our moments about A and see what happens. My rationale being, well, if moments about A didn't really give me what I needed, then we'd take moments about B and see if that was any better. So, like I say, as I said previously, just start blast down all the equations, see what happens, and see how all things start slotting together. So, moments about A. So we've got, going clockwise, we've got S, and we need the distance of the line of the force of S. So we need, there's the line of the force of S, and we need that distance away from A, so it's going to be that thing there. And again, I tend to draw some dotted lines in if it helps, but what we've got is the force times by the distance, which is 2a sine theta. So that distance there is our distance from the line of the force to our moment, 2a sine theta. And what have we got going anti-clockwise? Well, the anti-clockwise moment is going to come from the weight, so that's going to be 20g. And again, the distance we want is going to be this distance along here through the line to the line of the force. So that's going to be a cos theta. So we've got force times distance, 20g times by A cos theta. So that's that bit sorted. Now, here we go. Coming from our horizontal resolving equation, we've got S equals friction, and so that means we can just do a straightforward substitution into here, and that's why taking moments by A is going to work for us in this case, because it's the friction we're going to need to deal with. So there we go. We've got friction times 2A sine theta equals 20g times A cos theta, and so let's get friction now by just doing a bit of dividing, and we can tidy that up quite a bit, because we've got cos theta over sine theta, which is cot, or tan theta equals 3, so that means cot is going to be 1 over 3, so that bit there is going to be a third. We've got some a's cancelling out, 20 divided by 2 is 10, so the whole thing becomes 10g over 3. You can see we can have circled the 3 there, that's our 1 over 3, which is the cos over sine. Right, that's that bit sorted. So now we know that friction is 10g over 3, and we've got an equation up here. It says friction equals 20g times by mu, and bear in mind that mu is the thing we're finding, so hopefully we can see what's going to happen now. Put those two things equal to each other, do the divide by 20g, you get that. The g's will cancel, 10 over 60, 1 over 6, and there you go, you've got your coefficient of friction. Right, on we go, and let's have a look at an exam style question. So we've got a whole world of information here. Non-uniform rod, mass m, length 2L, rough horizontal floor, rough vertical wall. We've got an angle between the ladder and the rod and the floor, and we've got, as it turns out, two coefficients of friction. So as ever, let's whack all that into a diagram, and so we can start making sense of it. So here we go. There's my diagram. Non-uniform rod AB. Non-uniform, which means the centre of mass is not in the centre of the rod. So let's say we've got a distance of x to our centre of mass, and it's got mass m, so there's our weight, and I'll call that a point, that point G. Right, length 2L, there's that bit. Rough floor, so we've got friction. Rough wall, so we've got friction, again friction going up, so I've gone FA and FB to indicate my friction, my two different frictional forces at either end of the rod. Angle of 60 degrees, coefficient of frictions, let's just kind of add those, so there's our coefficient of friction between the rod and the floor is 1/4, between the rod and the wall is 2/3, so that's now here as well, so I'm putting all the information from my question into one place, into my diagram. And then the only other thing that we haven't put on the diagram at the moment that's not specifically mentioned in the question is, yep, it's the reaction forces. So we've got a reaction force between the rod and the floor, and a reaction force between the wall and the rod. I'm calling those R and S. So there we go. There's my diagram. Now, let's have a look at what we want. We want the magnitude of the vertical component of the force that exists on the rod by the floor. Now, we need to find R. There's a bit of a hint in this, because the thing for me is this: we've got this value x, which is missing. Now, this is only going to come into play when we start taking moments, but because we don't know it, because we're not yet being asked to find it, that tells me straight away that we're not necessarily going to need moments at the moment for this part of the question. So what I'm going to do is have a go at my vertical and horizontal forces and see if that works things out first of all. So here goes my horizontal forces. So we've got friction at A equals S. That's straightforward. And then my vertical forces, we've got R plus FB. They're the ones going up. The friction at B equals the mass which is going down. Okay, and we're going to need to find R. So what we're going to have to do is do a bit of work with the coefficients of friction. So F equals mu R. So we've got the friction at A, FA, is going to be 1/4 times R, and the friction at B is going to be 2/3 of S. Now, what we've got to do is get equation 2 just in terms of R. So because we need to find R, so let's try and get FB in terms of R, and we can do that by saying, well, taking those two facts there gives us S equals 1/4 R, and then taking the fact that our frictional force here, FB, is 2/3 of S, and we now know S is 1/4 of R, then let's bring that down and do some substitution into there, So now what that does is gives us the friction at B in terms of, slightly bizarrely, the reaction force at the bottom there, because all these things, as you can see, are kind of linked together. And so what we've got is our friction at B is 1/6 of R. So that then allows us to take equation 2. So I've taken the friction at B, replaced my 1/6 R. So here now I've got 7/6 of R. So therefore R is going to be 6/7 of mg. And there we go. There is our reaction force. Okay, the centre of the mass is at G. Find the distance AG. This is where we're going to need moments. So let's work out the distance x. So let's take our moments about A. So what have we got? I've just put in these extra dotted lines here to help me think about what's going on. So if I go clockwise, well, the only one we've got going clockwise is the weight. So force times distance, we've got mg times by the distance, which is going to be x, and it's this horizontal distance here, so x cos 60. And what's that going to equal? Well, the anti-clockwise ones are s and b. So let's have a look at s. The distance from the line of the force to my moment is going to be that distance there. So that's going to be 2L sine 60. And then the distance from the line of my frictional force to my moment there is going to be 2L cos 60. So I've got FB times by 2L cos 60, force times by perpendicular distance. Okay, so that's that all sorted. Let's do a bit of tidying up with our sine and cos 60s. So cos 60 is a half. So sine 60 root 3 over 2. So let's deal with that. Do a little bit more tidying up. We can see, oh, that 2 there is going to cancel against that one. We'll do some cancelling there. So now we've got an equation. We need x in terms of L, but we've still got S and F, the friction at B, FB. Now, if you think back to the previous slide, let's just have a look at what we had from before. Well, we had S equals 1/4 R, and R is 6/7 mg. So now that will be able to allow us to express S just in terms of mg by doing that. So that gives us S equals 3 over 14 mg. And we can do exactly the same with friction, because previously we had friction equals 1/6 of R, and therefore we need 1/6 times by 6/7, so we've got our frictional force is 1/7 of mb. So let's just express those things in terms of just of mg's. Replace them in our equation. Straight away you can see now we've got everything in terms of mg. So it turns out the weight of the ladder in this particular case becomes irrelevant. So what we've got now is an equation that looks like that. And what I've done there is just taken out the L, so I've factorised the L, so we've got root 3 over 14, 3 root 3 over 14 here, 1/7 there, and then all we've got to do is times that by 2, and we end up with that value, which is not a particularly nice surge. So in this particular case, it might say in the question give an exact value, or it might be say, okay, to 3 significant figures, in which case we've got 1.03 L. Right. The point behind that question was just to illustrate how, particularly in the first part, how we can just kind of start getting our equations, and then they all tend to kind of link with each other. So it's about seeing what we can replace from one equation into another to be able to trim things down to get them just in terms of one variable. And we saw that in part A and in part B. Right, let's move on and let's have a look at pegs, because that was the ladders bit dealt with. Let's have a look at pegs. Now, when we're talking about pegs, we're talking about basically circular objects, so pegs, barrels, everything of that kind. So we've got, in this example, a non-uniform beam, 4 meters resting on a smooth peg, and we've got the distance from one end to the peg, and all the information in the question. So let's just take that and turn that into a diagram. So just have a quick look at what we've got on my diagram there, and make sure you're happy with all the bits and pieces that are in the question. So the key idea here that we need to make sure we're quite happy with is the fact that the reaction force is going to be perpendicular to the beam, because essentially the reaction force is the normal, because the beam is a tangent to the circle at C. Obviously radius meets tangent at 90, so therefore the reaction force, which is perpendicular to the beam, is going to be perpendicular to the circle, and there we go. So that's why we've got our reaction force going in that direction rather than straight upwards. Okay, so that's the key idea, and that's going to have an impact on how we're dealing with our moments, because this one here is perpendicular, so our force here and our perpendicular distance is still going to be there, and we'll see that in a second. So let's take moments about A. As ever, I'm going to go clockwise first. So my clockwise moment is going to be coming from the mass, or sorry, or the weight of the beam. So we've got 5g, our force times by our perpendicular distance, which is going to be this distance along here, x cos 30. And our anti-clockwise moment is simply going to be 14 root 3 times by 3, because this, as I said, this is perpendicular, so that distance there, which we know is 3 meters, is our perpendicular distance from the line of the force through to the pivot. So that's what we've got, which leads us to finding x by just simply doing the divide, and that's the thing that we're after, and that becomes x is 12 over 7 meters. Like I say, key idea is this statement here that we've just kind of discussed. So on we go to part B, and in this case I need mu, so I'm going to need F equals mu r. So obviously when we talk moments by A, R and F just disappeared completely, so there's not going to be a lot of use there. So what I'm going to do now is just have a look at resolving horizontally and vertically and see what that gives me. So if I resolve horizontally, well, I've got friction going that way. Now, the other thing I've got to consider here is this force here is going neither horizontal nor vertical. It's actually going to have components going in both directions, so I need to see how much of my reaction force here is actually going horizontally. So to do that, let's just have a bit of a think about angles. We've got an alternate angle going on there. So the angle underneath the red line is going to be 30, which means the angle above that red line is going to be 60. So therefore, the amount of that reaction force going leftwards, in this case, is going to be 14 root 3 cos 60. And then if we have a look at what is happening vertically, all I've done here is just take the cos 60 as a half, that gives me 7 root 3. Vertically, we've got, what's going on? Well, we've got R plus, and again, it's going to be the reaction force coming here that's going to be vertical component, which is going to be 14 root 3 sine 60. And that is going to equal 5g. And that's a nice simple equation in terms of R. So a bit of rearranging and tidying up gives us R, as it turns out, is 28. Now, we are aiming for mu equals k root 3, where k is a constant. So let's go for F equals mu R, because we've now got F and R. Plug in the values that we had, do some dividing, and clearly there you go. We have got k equals a quarter. And there we go, that's that bit sorted. Right, last thing I need to do is just, I'm going to indulge myself. I suspect that this is the end of the video, so nobody's really watching it anyway, because you fast forwarded the whole thing. But that is my last video, done, sorted, recorded. I think that is 2 years worth of recording and around about 171 videos, all done and sorted. So a big woohoo! As now I think I'm finally done with my A-level videos. If you have watched them all, I hope they've been helpful and useful. They've taken a hell of a lot to do, but hopefully I think it's been well worthwhile.